What if your life never actually happened? What if the years you spent becoming who you are, the people who raised you, the mistakes you're still carrying around, none of it took place? What if you simply appeared a moment ago, already convinced that it had? There would be no warning to notice, no gap in your memory where the truth might slip through. A mind built this way arrives complete, holding a lifetime of memories it never had time to earn. Physicists have a name for that exact possibility. They call it the Boltzmann brain problem, a term coined in 2004 in a paper literally titled, "Can the Universe Afford Inflation?" It's a real, unresolved question in modern cosmology. It's serious enough that some of the same cosmologists who calculate the universe's long-term fate have had to ask whether their own math can be trusted at all. Cosmologists don't lose sleep over ghost stories. They lose sleep over unresolved variables sitting inside equations they otherwise trust completely. This is one of those variables, the kind that doesn't go away just because nobody likes where it points. This isn't a story about the universe ending. Endings are honest. They assume there was something real to end. What follows is stranger than that. The possibility that reality was always cheaper to fake for one lonely mind than it ever was to actually build, in full, for billions of us. The actual physics behind that claim starts with something you already understand without ever having thought about it. Heat. Start with your own hand. Skin, bone, blood, all of it feels solid, permanent, built to last. It isn't. Right now, at the atomic level, it's already unraveling. Heat is escaping through your skin. Cells are failing and replacing themselves imperfectly, and bonds between molecules are loosening in ways too small and too slow to feel. You were never finished. You've been mid-collapse since the day you were born, and so has everything else in the room with you. That's the second law of thermodynamics, and it doesn't negotiate. Pour milk into coffee and the swirl settles into an even brown within seconds, and it stays that way. You could watch that cup for the rest of your life and never see the milk and coffee separate themselves back out. The universe has exactly one direction it's willing to move in, toward mixing, toward evening out, toward less structure, never the reverse. The tendency has a name and it's younger than you'd think. A German physicist named Rudolf Clausius coined it in 1865, deliberately modeling the word on energy so the two would sit comfortably in the same sentence. He called it entropy. Despite how clinical it sounds, it's the plainest possible description of your own mortality. It's the reason a room never tidies itself. It's the reason a wound heals into a scar instead of healing back into unbroken skin. It's the reason every living thing you've ever loved is losing a fight that was rigged against it from the very first cell. There is, however, a loophole buried inside that same law. One most people go their whole lives without hearing about. Here's the loophole. Entropy increasing isn't a law in the same sense that the speed of light is, an absolute ceiling nothing can cross. It behaves more like a bet so lopsided it might as well be a law, right up until somewhere it isn't. In 1877, an Austrian physicist named Ludwig Boltzmann made the case plainly. Disorder isn't mandatory, only overwhelmingly likely. There are vastly more ways for a system to be messy than for it to be neat. Shuffle a deck of cards, and you'll get a meaningless jumble almost every time. A perfectly ordered deck isn't forbidden. It's just one arrangement out of an almost unimaginable number of possible arrangements, and the jumble wins by sheer weight of numbers. Most physicists at the time despised this idea, and it's easy to see why. They wanted the rules of the universe to be certainties, something you could stand on. Boltzmann was telling them something uncomfortable. One of the most fundamental feeling rules of all, that things fall apart and stay falling apart, was really just the safest bet in an enormous casino, dressed up to look like a law of nature. And a bet, unlike a law, can still lose, which raises an uncomfortable question. What happens if you let that bet run for long enough that losing stops being a possibility and starts being a certainty? So let that bet run for long enough. Not a human lifetime. Not the age of a civilization, but a span of time so vast that billions of years stops being a useful unit. It's the same way a ruler stops being useful once you're measuring the distance between galaxies. At that scale, the absurdly unlikely stops behaving like something that merely could happen and starts behaving like something that will. Every arrangement of particles permitted by the laws of physics, however improbable, eventually gets its turn. Not because the universe wants it to, but because eventually is an extraordinarily patient word, and improbable things are still, technically, things that happen. Boltzmann saw exactly where this leads, and said so in writing in 1895, in a letter to the journal Nature. He credited the idea to an assistant of his, a Dr. Schutz, but the argument was his to defend. The claim that the ordered, structured universe we live in might not be the product of any grand cosmic plan, but a random statistical fluctuation. A lucky, temporary clump of order assembled out of an otherwise dead, featureless equilibrium cosmos purely by chance. The same way our example room might, once in an unthinkable while, fluctuate into a corner full of trapped air. And if an entire universe's worth of order can fluctuate into being by pure chance, the fluctuation doesn't have to be that large to work. A single, isolated, self-aware mind, its head already full of memories it never actually lived through, would be a far smaller, far cheaper thing for chance to produce than a whole cosmos. Far more statistically forgiving too, including quite possibly the one reading or hearing these words right now. That's not a fringe idea whispered at the edges of physics. It has a formal name, a real research history, and its own uncomfortable shorthand in academic papers: the Boltzmann brain problem. It resurfaced in 2002 when physicists Lisa Dyson, Matthew Kleban, and Leonard Susskind published a paper whose title doesn't try to soften the blow: Disturbing Implications of a Cosmological Constant. They weren't writing horror fiction, they were doing the math on what our universe's long-term fate actually implies about the kinds of minds that should exist within it. And the math kept landing somewhere nobody particularly wanted it to land. Physicist Sean Carroll has spent years working out what to do with that result. His concern was never that you, personally, are a randomly assembled brain flickering in the dark. It's that any serious model of the universe predicting most of its observers should be exactly that kind of accident has a serious problem on its hands. Either the model is broken, or something we don't yet understand is quietly keeping it from being true. That's the argument we're about to walk through, piece by piece, in the order the physics actually demands. It starts from the plainest fact in the whole field. Heat only ever flows in one direction. Heat only flows one way, from hot to cold, never the reverse, not once, not anywhere, not ever. Physicists call this the second law of thermodynamics, and it is the single most tested, most unbroken rule in all of science. Your hand, right now, is quietly following it. Heat leaving your skin into the cooler air, atoms shifting toward whatever state has more ways of existing than the one before it. That process has a direction. It never runs backward. The person who first pinned this down wasn't chasing the fate of the universe. His name was Sadi Carnot, a French military engineer. In 1824, he sat down to answer a narrower, dirtier question. Why do steam engines always waste fuel, no matter how well they're built? His answer became the seed of everything that followed. Heat cannot be converted entirely into useful work. Some of it always leaks away, flowing from hot to cold, and no design, however brilliant, closes that gap to zero. Decades later, Rudolf Clausius and William Thomson, later Lord Kelvin, took Carnot's stubborn little fact about pistons and expanded it into a claim about the entire universe. Heat flows one direction, structure degrades into disorder, and this isn't a tendency, a preference, or a rule of thumb. In 1928, the physicist Arthur Eddington called it the supreme position among the laws of nature. and warned that any theory contradicting it deserves nothing but deepest humiliation. That's not scientific enthusiasm. That's how seriously physics takes this rule. Seriously enough that it bends everything else around it, your hand included. Which means the thing happening to your hand right now, to every cell in your body, to every star burning overhead, is not decline. It's obedience. You are not falling apart by accident. You are following the most rigorously confirmed law physics has ever produced, and it has never once, anywhere, made an exception. That exceptionless rule needs some way of being measured, and that's exactly what entropy is. Not a mood, not a metaphor, but a literal count of arrangements. A tidy room has almost no arrangements that still count as tidy. A messy one has nearly infinite arrangements that still count as messy, which is exactly why messy wins, every time, without needing anyone or anything to make it happen. Ludwig Boltzmann proved this with mathematical precision in 1877, turning a decades-old philosophical worry into hard, countable numbers. It should have made him untouchable. Instead, it's carved onto his own gravestone, in Vienna's Zentralfriedhof, its central cemetery in the form of a short, elegant equation. Entropy equals a constant, multiplied by the logarithm of the number of ways a system's pieces can be arranged. From a distance, that grave looks like a monument to a man who won completely. Get closer, and the story sours. The specific constant baked into that equation, the one the whole world now calls Boltzmann's constant, was never his. It was added years after he died, by Max Planck, solving a completely unrelated problem in 1900. Planck admitted as much himself, in his own Nobel lecture in 1920. As far as he knew, Boltzmann never used the constant that now carries his name into eternity. So the equation on the stone isn't really his signature. It's someone else's handwriting, forged in his honor on a grave he can no longer argue with. A strange, quiet way for the universe to remind you that even the man who mapped out exactly how everything falls apart didn't get the final word on his own ending. Boltzmann never got the final word on his own story. Neither, it turns out, does the universe. Take the same one-way rule, hot to cold, order to disorder, and run it across everything that exists. Not just a hand, not just a headstone, not just one dying star. Run it far enough and you arrive somewhere physicists have a specific name for: heat death. Every star eventually burns out. Every black hole, given enough time, evaporates too. Even the largest ones, over a timescale so long that physicists write it as 10 to the power of 100 years. Every last scrap of usable energy spreads itself so evenly across space that nothing remains capable of doing anything at all. No motion worth the name, no temperature difference left to power a single further event. Just a structureless equilibrium, stretching on with nothing left to interrupt it, forever. That name isn't new either. Rudolf Clausius, the same physicist who coined the word entropy in 1865, gave this exact ending its own name that same year, in German, Vermitode. Physicists have expected this fate for over a century and a half. What's changed is that we can now actually watch it starting to happen. In 1998, two teams of astronomers were tracking a kind of exploding star called a Type 1a supernova. One team was led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees. It's bright and consistent enough to work as a reliable distance marker across billions of light years. The supernovae kept turning up fainter, and therefore farther away, than a universe slowing down under its own gravity could explain. Both teams reached the same unplanned conclusion. The universe's expansion isn't slowing down, it's speeding up. The finding reshaped cosmology so thoroughly that all three scientists shared the Nobel Prize in Physics in 2011. It's the same result feeding directly into today's predictions of exactly this kind of ending. Right now, buried in the equations describing your own future, a number is counting down toward a moment with no observer left standing to notice it arrive. And as staggering as 10 to the power of 100 years already sounds, file it away. It's about to look almost modest by comparison, right after one piece of unfinished business. There's a piece of this story we skipped, and it matters because Boltzmann's probability argument wasn't a calm discovery handed to him in a moment of clarity. It was a forced retreat. In 1876, his own friend and colleague, the Austrian physicist Joseph Loschmidt, handed him an objection that should have ended the whole idea before it properly started. Loschmidt's point was simple and, on its face, devastating. The fundamental equations of physics are time-symmetric. Run them backward, and they still work perfectly, describing a universe that would look just as valid running in reverse. So, take a gas that has just settled into equilibrium and mathematically reverse every single particle's velocity. The same trusted equations predict something strange. The gas should unmix itself, sliding right back toward the ordered state it started from. Reversible laws, Loschmidt argued, cannot possibly produce an irreversible universe. For a while, it genuinely looked like Boltzmann's entire framework might not survive the year, undone by his own friend. He answered the following year in 1877, and the answer still holds up today, unbroken. Loschmidt was right about the equations and wrong about what they meant. Reversing a gas back into order isn't forbidden. It's just staggeringly unlikely. One specific needle buried inside an incomprehensibly large haystack of possible arrangements. It's so small that watching for it across an ordinary human lifetime would show you nothing at all. Not even a flicker. Loschmidt had tried to disprove Boltzmann, and ended up proving something stranger than either man expected. That order climbing back out of chaos was never actually forbidden. Only so rare that, until someone finally did the math, impossible was the only word anyone had for it. Rare is doing a lot of quiet work in that sentence, though. The gap between rare and impossible is exactly where the rest of this theory lives. A gap wide enough, it turns out, to fit an entire universe of implications inside it. Take every air molecule in the room around you right now. They're spread out, bouncing around at random, the way they always are. Nothing in physics forbids them from all drifting into one corner and staying there, leaving you gasping in a sudden pocket of vacuum. It's allowed. It's just so wildly improbable that you could watch this room for the rest of your life and your children's lives and never once see it happen. But wildly improbable is not the same word as never. Wait long enough, and the room does it anyway. Exactly once, exactly on schedule. Now stretch that same bet from a room full of air to an entire universe of empty space. Run it for far longer than the 10 to the power of 100 years it takes for heat death to finish. The numbers stop being difficult to believe and start being difficult to even hold in your head. Physicists studying an empty, expanding universe have estimated the timescale for assembling a single, stray, self-aware mind out of pure, random noise. The number they arrive at is 10 to the power of 10 to the power of 50 years. For comparison, the universe as measured by the Planck satellite is about 13.8 billion years old. Set those two numbers side by side. The age of everything that's ever happened, every war, every civilization, every sunrise, doesn't even register as a rounding error against the weight. It's not that the odds are against you, it's that given enough time, they stop being odds altogether and start being a date already circled on a calendar nobody can see. A date that far out only makes sense if empty space genuinely never stops moving, even after everything else has gone still. And it turns out it doesn't. You'd expect a perfect vacuum, especially one sitting inside a universe expanding forever, to eventually go completely, permanently silent. Zero temperature, zero activity, nothing left to disturb it. In the 1970s, physicists Gary Gibbons and Stephen Hawking showed otherwise. Empty space in an expanding universe carries a faint, non-zero temperature of its own, one dictated directly by how fast that expansion is happening. The mechanism is the same one Hawking had already found lurking at the edge of a black hole. Any horizon, the boundary of a black hole, or the boundary of how far you can ever see in an accelerating universe, quietly radiates simply by existing. It's the same Hawking, working from the same physics, who showed that even black holes slowly leak radiation and evaporate. That's the 10 to the power of 100-year process, already sitting in the background of everything we've covered so far. Nothing in this universe, it turns out, gets to be perfectly, permanently still. Not even nothing. That detail is doing more work than it sounds like it should. A temperature above absolute zero means the vacuum is never fully quiet. It's always faintly jittering, the way a pot of water well below boiling still trembles at the surface, long before it ever earns the name boiling. That faint, eternal jitter is the actual mechanism, not a metaphor, that allows something as complex as a passing thought to assemble itself out of nothing, given enough time to try. The room from a moment ago was never really sealed off from any of this. It was just a smaller, faster rehearsal of the exact same restless universe already surrounding it, running the identical bet on a much shorter clock. Same bet, shorter clock, but stack the three pieces together. A universe trending toward heat death, a vacuum that never goes fully quiet, and stretches of time long enough to make the improbable routine. Put them together and you don't get a ghost story. You get a specific, mathematical description that increasingly looks like it could apply to the actual future of the actual universe you live in. That's exactly why physicists haven't been able to shrug this off as a curiosity, the way you might dismiss a fun fact at a dinner party. Suppose a cosmological model predicts that stray, isolated fluctuations should vastly outnumber observers who arrived through ordinary cosmic evolution. Most cosmologists treat that prediction as a warning light on the dashboard, not a footnote. That doesn't mean the model is definitely wrong. It means something in that specific model, or in the argument built on top of it, still needs fixing before anyone trusts what it predicts. It is a strange kind of scientific honesty, using the sheer horror of a result as a diagnostic tool, a way of testing whether your own equations can still be trusted. An entire field of serious researchers treats too horrifying to be true as an actual, technical reason to go back and check the math. Not because horror is evidence of anything on its own, it's because a universe that mostly produces confused, isolated, memory-fabricating minds is a universe whose physics has probably gone wrong somewhere upstream. This one does because the man who first did the underlying math never got to see where it led. He built the tool, then vanished from the story before anyone had the chance to point it at the stars. He vanished, in fact, in a way that shapes everything the next part of this story is about to show you. He vanished the way certain people do, not suddenly, but through a long, well-documented unraveling that the people around him watched happen in real time. His name was Ludwig Boltzmann, and by the time this story catches up with him, he had already spent decades building the mathematics you've just spent 20 minutes inside of. Those closest to him described something specific. Not vague sadness, but sharp, repeating swings. Stretches of restless, almost manic productivity gave way to collapses into a depression severe enough to frighten his family. Historians looking back on his letters and behavior now suspect what would today be diagnosed as bipolar disorder, decades before anyone had a clinical name for that either. He wasn't a tragic figure by temperament. He was, by every account, warm, funny, a genuinely beloved teacher. The instability came and went on its own schedule, indifferent to how good or how difficult his life happened to be at any given moment. That instability might have stayed a private matter. It didn't, because Boltzmann spent the better part of his career defending an idea that most of his most senior colleagues considered close to heresy. That atoms were real, physical objects, not just a convenient mathematical fiction. And the people fighting him on it weren't cranks at the edges of the field. They were some of the most respected physicists and chemists in Europe. That fight is where the real war started, and it's the war that eventually broke him. The war had a name, even at the time: energetics versus atomism, and it split European physics for the better part of 2 decades. The energetic side, led by the chemist Wilhelm Ostwald and the physicist-philosopher Ernst Mach, argued that atoms were an unnecessary hypothesis. Everything observable, they said, could be described purely in terms of energy, without ever assuming matter was secretly made of tiny, discrete particles no one had ever directly seen. Boltzmann thought this wasn't just wrong, but backward. The two sides collided in public, most famously at a scientific conference in Lübeck in 1895. Boltzmann and the mathematician Felix Klein faced off against Ostwald and his ally Georg Helm, with physicists like Walter Nernst and Arnold Sommerfeld watching from the room. Sommerfeld himself described the clash in a single unforgettable line. The fight between Boltzmann and Ostwald, he wrote, resembled the struggle between a bull and a supple fencer. Boltzmann was the bull. Raw force, momentum, conviction, and by every account, it carried the room that day. Winning didn't end anything. The attacks kept coming for years afterward, in journals, in lecture halls, in the quiet social machinery of academic reputation. Boltzmann, already prone to those sharp swings in mood, absorbed every round of it personally. Victory on paper never once translated into peace. Here's the version of this story most people already believe, the one repeated in physics classrooms and popular science books alike. That Boltzmann was mocked, isolated, and driven to his death by a scientific community that refused to take him seriously. It isn't true, not the way it's usually told. By any objective measure, Boltzmann was one of the most recognized physicists of his era. In 1888, he was offered a prestigious chair in Berlin and turned it down. Universities in Leipzig, Munich, and Vienna competed openly for him, dangling salaries most professors could only imagine. He collected medals, honorary doctorates, invitations. The energetics fight was real, and it was ugly, but historians who have gone back through the record find no evidence that he was ever genuinely ignored. What actually wore him down ran deeper than citations or conference debates. In notes from one of his own lectures from October 1904, reconstructed by historians from his teaching materials, Boltzmann can be found wrestling with something close to a warning about himself. Philosophy, he said, got on his nerves because analyzing the ultimate ground of everything eventually made everything fall into nothingness. He decided to keep teaching anyway, to look the hydra of doubt straight in the eye. As a joke, he added that doing so could be quite ominous if one values one's life. He kept teaching, but the popular version of his death still needs a villain, still needs a clean morale about a genius rejected by his peers. That might be the most on-theme detail in this entire story. Even the tragedy of the man who studied how order quietly collapses into disorder has been reassembled after the fact into a tidier shape than what actually happened. That private unraveling had already surfaced once before, 6 years earlier, and almost nobody outside his immediate circle knew about it. In 1900, while working in Leipzig, Boltzmann made his first attempt on his own life. He survived it, returned to his lectures, and the ordinary rhythm of his career resumed, almost as if nothing had happened. The standards of the time offered little in the way of real intervention for what he was actually going through. 6 years later, in early September of 1906, Boltzmann traveled with his wife and daughter to Duino, a small coastal town near Trieste. It was meant to be an ordinary family holiday by the sea. On September 5th, while his wife and daughter were out swimming in the water nearby, Ludwig Boltzmann died by suicide. He was 62 years old. There is no tidy explanation for exactly why that particular day, in that particular place, became the end. And as we've just established, this isn't a story that needs one final villain to make sense of it. What the record actually supports is a private, years-long struggle that had nothing to do with atoms, entropy, or academic rivalries at all. Physics didn't kill him. It simply never got the chance to hand him the one piece of vindication that might, conceivably, have helped him keep going a little longer. The one piece of proof he never lived to see arrived almost immediately after he was no longer alive to receive it. It was proof that the atoms he'd spent his whole career defending were real, physical things, not just a convenient trick of the math. And it started, unexpectedly, with Albert Einstein. In 1905, in one of several papers that would define his early career, Einstein worked out a precise mathematical prediction. If atoms existed, he argued, they should cause microscopic particles suspended in a liquid to jitter and drift in a specific, measurable pattern, a phenomenon known as Brownian motion. 3 years later, the French physicist Jean Perrin took that prediction into the lab, using a microscope to track the actual, visible path of single microscopic particles suspended in water. What he watched, plotted position by position every few seconds, was a jagged, twitching, directionless zigzag. It was motion with no visible cause and no visible pusher, as if the particle were being struck at random from every side by something nobody could see. That something was exactly what Boltzmann had always insisted was there. Countless invisible water molecules colliding into the particle by pure chance, thousands of times every second. Perrin used the pattern of that trembling, aimless dance to calculate the actual physical size of atoms, with testable precision anyone could check. Atomism had won, decisively, on data anyone could reproduce. The result was so conclusive that Wilhelm Ostwald, Boltzmann's most persistent opponent, publicly recanted his own position in 1909. In 1926, Perrin received the Nobel Prize in Physics for exactly this achievement. Boltzmann missed all of it by 2 or 3 years. He had already told people, long before any of this, what he believed his job was. Bring forward what is true, write it so that it is clear, defend it to your last breath. He did exactly that for decades, without ever finding out he had actually won. He never found out he'd won, and in a strange way, the argument he built has kept winning ever since, in places he could never have imagined it would travel. The same statistical reasoning that explained why a room full of gas tends toward disorder. The same math that explained why atoms jitter under a microscope didn't stop at atoms. A century later, it became one of the working tools cosmologists use to describe the fate of the entire universe, including the exact scenario this story opened with. That's not a loose metaphor or a cute callback. The equations describing statistical fluctuations, the ones Boltzmann fought Loschmidt and Zermelo over, the ones carved incorrectly onto his own gravestone, are structurally the same equations physicists use today. They calculate how often a stray, self-aware mind should assemble itself out of empty, expanding space. He built the hammer out of nothing but probability and patience. He had no way of knowing what would eventually get built with it, or how far from a room full of gas the argument would eventually travel. To get from his equations to that conclusion, though, cosmology needed one more piece, something Boltzmann himself never had any reason to think about. It's a universe that doesn't just sit there existing, but expands, and keeps expanding, at a rate that changes everything about how the odds get counted. That piece arrived in a lab in California on an ordinary Thursday night, decades after his death. Which brings this story back, 100 years and several branches of physics later, to the question it actually opened with. Except now you have the tools to understand exactly how seriously it's meant, and how much further the same logic is about to stretch. 100 years is a long way for an idea to travel, and the version of Boltzmann's argument physicists use today starts almost nowhere near a room full of trapped air. It starts, instead, with a single physicist working late on an unglamorous problem. By morning, he had scrawled 2 words across the top of his own notebook, in block capital letters, as if he needed to convince himself of what he'd just found. On the night of December 6th, 1979, a young physicist named Alan Guth was chasing something far narrower. Why doesn't the early universe contain a specific kind of exotic particle, called a magnetic monopole, that older models predicted should be everywhere? A magnetic monopole is a hypothetical particle with only one magnetic pole, a north without a south, something no magnet anyone has ever built or found in nature actually has. The leading physics of the day, grand unified theories, predicted the early universe should have produced them in huge numbers. Nobody, then or since, has ever detected a single one. Chasing that mismatch, Guth stumbled onto something far bigger. The two words at the top of his notebook, the ones that still sit in a museum in Chicago today, read, "Spectacular realization." What he'd found was a strange, temporary condition physicists call a false vacuum. Not empty space at its true lowest energy, but a field caught higher up, resting in a shallow dip on a hillside instead of rolling to the bottom. Plugged into Einstein's equations, that condition does something no ordinary form of matter does. Its pressure turns negative, and negative pressure doesn't pull things together the way gravity always has. It pushes things apart instead. Space itself gets shoved outward, doubling in size, then doubling again over and over in a span of time too short to properly call an instant. By then, it had stretched by a factor of at least 10 to the 26th power, in a trillionth of a trillionth of a trillionth of a second. It solved Guth's original monopole problem outright, and two others nobody had even been trying to solve. Why does the universe look so flat, and so nearly identical in every direction we point a telescope? 3 stubborn puzzles, 1 mechanism. There's something almost too fitting about that word, false. A vacuum pretending, for the briefest possible instant, to be the true, settled foundation of everything, before dropping through into what was actually underneath it the whole time. We'll be coming back to that word. Because the false vacuum came with a side effect nobody had planned for, one that would eventually matter more than magnetic monopoles ever did. In most versions of this theory, once it starts, inflation doesn't seem to want to stop. Doesn't want to stop is doing a lot of work in that sentence, and it's worth taking seriously. The physicists who followed up on Guth's idea kept finding the same uncomfortable result from different directions, using different methods, arriving at the same place. In 1983, the physicist Paul Steinhardt showed the first working example of inflation that never fully ends. Alexander Vilenkin then demonstrated this wasn't some special case dreamed up to make the math interesting. Under very general conditions, eternal inflation turns out to be the default outcome, not the exception that needs explaining. Across 1982 to 1986, the physicist Andre Linde developed his own version, one he called eternal chaotic inflation. In it, inflating space keeps expanding forever, endlessly spinning off separate regions where inflation locally stops and cools. Each one settles into something that looks, from the inside, exactly like an ordinary universe, full of stars and rules and history. Our own observable universe on this picture is just one of those cooled off pockets. One bubble among an uncountable, still growing number of others. Each one is sealed off from the rest by the same runaway expansion that produced it. There's a catch buried inside all of this, worth pausing on before moving further. In 2003, the physicists Arvind Borde, Alan Guth, and Alexander Vilenkin proved something that cuts against the word eternal in the other direction. Any universe that has, on average, been expanding throughout its history cannot stretch back infinitely into the past. It has to have a beginning. Eternal inflation, it turns out, is only eternal going forward. Trace it backward far enough, and the theorem says you hit a genuine edge, a boundary nobody has found a way around. One of those separate, cooled-off regions, if this picture is right, is the one you're currently sitting in. And the same bet that once applied to a single room full of air now applies, without modification, to an entire bubble universe. It applies to every mind that will ever exist inside it, including the one reading these words right now. Guth's original theory solved plenty, but it had one nagging flaw. Figuring out exactly how inflation ends turned out to be far harder than starting it. That gap is what physicist Andre Linde closed, first in 1983, then again more radically in 1986. Linde's version, called chaotic inflation, dropped Guth's original assumption that the whole early universe switched inflation on and off at once, everywhere, together. Instead, Linda argued, different patches of space carry different starting values of the field driving inflation. Picture a stormy ocean, where wave heights vary unpredictably from one patch of water to the next. Some patches never get high enough to inflate at all. Others get shoved to enormous heights and take off, stretching by unthinkable factors before finally settling into something that looks, from the inside, like an ordinary universe. 3 years later, Linda pushed the idea further still, into what he called eternal chaotic inflation. The field driving inflation keeps fluctuating randomly as space stretches. Some of that still inflating space keeps generating brand new patches high enough to inflate all over again, faster than any of them can finish settling down. The process never runs out. It keeps producing new, disconnected pockets of ordinary universe forever, each one sealed off from every other by the same runaway expansion that built it. Instead of a universe with a single law of physics, Linda has said, eternal chaotic inflation predicts a self-reproducing, eternally existing multiverse where all possibilities can be realized. All possibilities, not most of them. Not the convenient ones. Every physically allowed variation of a universe generated somewhere, endlessly, forever, including, should the numbers work out that way, every possible variation of the exact thought you're having right now. An endlessly self-reproducing multiverse solves several deep problems in cosmology. It also resurrects the exact problem this story already introduced you to, except now the numbers get almost unmanageably worse. Alan Guth, the same physicist who wrote Spectacular Realization in his notebook back in 1979, has spent decades since then confronting what he calls the measure problem. He likes to explain it using cows. In a single universe, cows born with 2 heads are rarer than cows born with 1 head, Guth has said. But in an infinitely branching multiverse, there are an infinite number of 1-headed cows, and an infinite number of 2-headed cows. What happens to the ratio? Ordinary arithmetic has no answer for that. Infinity divided by infinity isn't a number. It's a warning sign. That warning sign matters enormously here, because in an eternally inflating multiverse, both kinds of observers get produced in infinite number. There are the ones who evolved the ordinary way through billions of years of stars, planets, and biology. And there are the ones who assemble for a moment out of random thermal noise. Comparing 2 infinities requires choosing a rule for counting them first, and different, individually reasonable-looking rules produce wildly different answers. One of the most naturally chosen rules, called the proper time cutoff, produces a result physicists nicknamed the youngness paradox. Run the numbers, and an observer in a universe our exact age gets vastly outnumbered by observers in a universe only slightly younger. The factor is staggering for every fraction of a billion years shaved off. Follow that logic all the way down, and the most common observer this rule predicts isn't anything like you. Researchers call it a Boltzmann baby, a fleeting, randomly assembled mind, popping into existence out of the hot, chaotic conditions of the very early universe. It holds memories of a life it never lived, for exactly as long as the fluctuation that made it happens to last. Guth didn't shrug this off as a curiosity either. In 2010, Guth co-authored a paper alongside physicists Andrea de Simone, Andre Linde, Mahdia Nourbala, Michael Salem, and Alexander Vilenkin. Its title reads almost like a confession: Boltzmann brains and the scale factor cutoff measure of the multiverse. The man who discovered inflation spent part of his career trying to stop his own theory from concluding that people like him shouldn't exist. Their proposed fix, a different way of counting called the scale factor cutoff, does manage to dodge the worst of the youngness paradox. But the fix turns out to sit on a knife edge. Nudge the counting rule's central parameter one way, and the youngness paradox comes right back. Nudge it the other way, and you land in what researchers call the opposite failure, an oldness paradox. Nearly every observer the theory predicts turns out to be a Boltzmann brain after all. just arriving from the other side of the same ledger. Not every serious attempt takes the same route either. The physicist Raphael Bousso built an entirely different kind of measure called the causal diamond out of black hole physics rather than trying to patch the cutoff directly. It sidesteps some of the worst tuning problems the other measures run into, and it makes a few real, checkable predictions about our own universe that turned out to match observation. It also comes with its own unresolved edge cases, including how to handle universes with a negative cosmological constant. Different tool, same unfinished job. No version of the measure physicists have tried gets to skip this choice entirely. Tune the counting one way, and you drown in Boltzmann babies. Tune it the other way, and you drown in Boltzmann brains. There isn't yet an agreed-upon rule that avoids both traps at once. Dozens of proposed fixes exist, and by Guth's own admission, few physicists consider the underlying problem solved. Which is precisely why this was never a ghost story dressed up as physics. It's a live, unresolved argument sitting inside working equations, built and defended by the same people who built the theory in the first place. They're still checking, right now, whether the universe they discovered has quietly made you one of its accidents. All of this stays comfortably abstract until you let one image sit for a moment. It's the image Andre Linde himself reaches for when he tries to describe what living inside a self-reproducing multiverse actually feels like from the inside. Parallel lines can intersect far enough away, Linde has said. The laws of physics can change. We just can't see it when they do. We're ants on a vast balloon. Take that seriously for a second. An ant walking across the surface of an inflating balloon experiences its own patch of rubber as flat, stable, permanent. The only reasonable way for a surface to be. It has no way to feel the curve. It has no way to sense the far side, or the seam, or the hand still blowing air into the whole structure. Its entire working model of reality is accurate, locally, and completely blind to everything that actually explains it. It's worth noticing the irony baked into that image because it circles back to something concrete from earlier in this story. The universe you can actually observe from Earth measures out flat, edge to edge, in every direction our best instruments can check. That flatness was one of the very problems inflation was invented to solve. If Linde is right, that flatness isn't evidence there's nothing more to see. It's exactly what an ant would report, standing on a balloon large enough that its own patch never shows the curve. That's not a metaphor about the multiverse in general. It's a description of exactly where you're standing right now. Reading or hearing these words. Inside a bubble, you have never once been able to step outside of to check. Every instrument you've ever built, every experiment you've ever run, every memory you've ever trusted, was assembled entirely within the ant's eye view. None of it was ever built to detect the curve. So where does that leave the hypothesis quietly built up over the last 20 minutes? Not proof. Physicists have been careful, consistently, not to claim that. What the measure problem actually establishes is narrower, and in its own way, more unsettling. Nobody currently has a rule for counting infinite observers that avoids predicting an excess of exactly the kind of mind this story opened with. Not without simply being tuned, after the fact, to dodge that specific conclusion. That's the honest shape of where modern cosmology actually stands. Physicists treat an overabundance of Boltzmann brains the way a structural engineer treats a bridge design that predicts its own collapse. Not as confirmed doom, but as a diagnostic failure serious enough to send everyone back to the blueprints. The scale factor cutoff you just heard about, Bousso's causal diamond, and half a dozen other proposed corrections all exist purely to make this problem go away. None of them have succeeded cleanly yet. This is the same test Sean Carroll described earlier in this story. A theory predicting an excess of Boltzmann brains isn't making a claim about ghosts. It's failing a basic test of self-consistency, and it needs fixing or abandoning, regardless of how uncomfortable the fix turns out to be. So the honest answer to the question this story opened with isn't yes, and it isn't no. It's that the tools currently available to physics cannot rule it out. The people holding those tools include some of the same names responsible for building modern cosmology in the first place. If the argument stopped there, you could file it under unresolved physics and move on with your evening. It doesn't stop there. This exact move, betting on whichever version of reality lets someone survive to check the math, has been tried once before. The target that time had nothing to do with minds at all, and it came back with a verified, checkable, dead right answer. In 1987, a physicist did something that shouldn't have worked. Before anyone had built an instrument precise enough to test him, he wrote down a number. A cosmological constant no larger than roughly 500 times the density of matter filling today's universe. It was the exact strength of the force currently pulling every galaxy in the sky apart from every other. The same sky stretching thin over your own head right now. Then he waited. His name was Steven Weinberg. His target wasn't a mind. It was the invisible pressure stretching the entire universe thin. The same pressure this story has already blamed for the empty, cooling future waiting at the end of everything. Here's the strange part. Weinberg never measured that pressure. He reasoned about it using a version of the same cold arithmetic already turned on you a few minutes ago. If that force could have taken almost any value at all, most of those versions spelled trouble. Space would have torn itself apart too violently for a single galaxy, star, or living thing to ever form. Only a narrow band of values allows anyone to exist at all, and ask the question in the first place. So Weinberg bet on that narrow band. Get the number wrong and there's no drama, no story, no you, listening to this sentence. Every version of the universe on the wrong side of that line failed silently, unwitnessed, with nobody left standing to notice it had even happened. A decade later, in 1998, astronomers finally measured it. The number landed exactly inside the band Weinberg had marked out, years before anyone had a telescope capable of checking. He'd bet on the only kind of universe capable of producing a reader for his own paper, and he won. Which means somewhere, right now, the same bet is quietly running again. Just not on a number this time. The uncomfortable answer, on you. Physicists run this exact math to compare two kinds of minds. One built slowly, over billions of years of evolution. One assembled in an instant, out of pure chance, inside a fluctuating vacuum. Count how many of each kind should exist across an unfathomably large or eternal universe, and the numbers don't stay close. They collapse toward the random kind by a margin too large to comfortably write out. That's the identical weighing Weinberg used on the cosmological constant. Same engine, different question. Pointed at gravity, and it landed on a number the universe confirmed a decade later. Checked against a real sky full of real galaxies. Point that same engine at the population of minds scattered across an eternally inflating universe, and it lands somewhere else. On you. Statistically, the accidental kind. Sean Carroll, the physicist already worried about what an excess of these accidental minds means for cosmology, has spent years pointing to exactly this kind of case. Weinberg's success is exactly why he refuses to let anyone dismiss this kind of math as clever but untestable. It already produced one number reality confirmed, 500 times, give or take, and reality landed inside it. Nobody gets to trust it there and wave it off here. Not when here means whatever is currently doing your thinking, which would be a tidy, horrifying place to leave it. Except the constant this entire bet depends on may not be constant at all. The ground this argument has been standing on might already be shifting, silently, underneath it. For decades, every calculation behind the heat death, the endless dark, the impossibly long wait for a stray mind to flicker into being, rested on one buried assumption. That the force tearing the universe apart never changes. A true constant, fixed, forever. That assumption just cracked. In 2024 and 2025, an instrument called DESI mapped tens of millions of galaxies from a mountaintop in Arizona, tracking how fast space has stretched apart over 11 billion years. Combined with older supernova data, the results pointed at something nobody had built into the earlier math. The force is weakening, not vanishing. Weakening at a confidence of 4.2 sigma, real, but just short of the 5 sigma bar physics demands before calling anything proven. Weaken far enough, for long enough, and the ending changes shape entirely. Some analyses built on this same result point toward the pulling force reversing, gravity finally winning, expansion slowing, stopping, folding back in on itself. Not in 10 to the power of 100 years, not 10 to the power of 10 to the power of 50. Some estimates put it as soon as 20 billion years from now, a number almost small enough to feel close. Nobody currently knows which future is actually waiting. Maybe the slow fade already measured in the coldest, emptiest reaches of expanding space. Maybe a sudden collapse, arriving on a calendar short enough to stop feeling abstract. Either way, the countdown that once needed nothing more than a room full of trapped air now runs on the scale of the whole sky, and it's still counting toward you. Not every physicist believes that number. 4.2 sigma sounds precise, almost final, the kind of figure people stop arguing about. It isn't. Swap the supernova catalog underneath it for a different one, and the number moves. Combine DESI with a catalog called Pantheon Plus, and the same underlying data drops to 2.8 sigma. Swap in a catalog called Union 3 instead, and it climbs to 3.8. Only the newest catalog, DES-SN5YR, pushes it up to 4.2. Physics has a stricter bar for calling something proven, 5 sigma, the same threshold that had to clear before anyone was allowed to say, out loud, that the Higgs boson was real. Nothing about a weakening cosmological constant has cleared that bar. Not close, not yet. In 2025, 2 cosmologists, Deng Wang and David Motor, went back through DESY's own numbers and found something messier sitting underneath the headline result. The datasets being combined, the microwave background, the galaxy survey, the supernovae, don't fully agree with each other to begin with. Stitch disagreeing data together, they argued, and the resulting number stops meaning what it looks like it means. Their own conclusion wasn't a simple no either. Taken one at a time, none of the individual datasets detects the acceleration change confidently on its own. Taken together in their own separate analysis, the evidence for a changing universe still came out ahead. Nobody currently agrees on why. Nobody currently agrees on how much that should worry you. What both sides agree on, oddly, is what's actually at stake. If the number holds anywhere near where Deci put it, heat death may not be the ending waiting at the end of everything after all. Which means, for the first time in this entire story, there might be a way out. Whether that counts as good news is a different question entirely. Take that seriously for a moment, and something almost like relief opens up. The entire Boltzmann brain calculation, the one this story spent its first hour building, only works if the universe keeps going forever. Every stray, randomly assembled mind needs an ocean of time to fluctuate into existence. 10 to the power of 10 to the power of 50 years. A number too large to compare to anything real. A universe that ends in 20 billion years, folding back into itself, never gets anywhere close. Cut the clock short enough, and the odds of you being one of those accidental minds don't just shrink. They round down to nothing. Hold on to that relief for just a moment. It only closes one door. Everything just described happens inside a single bubble. One pocket of space among however many the earlier eternally inflating multiverse produced. Andre Linde's eternal chaotic inflation, the mechanism this story already walked through, doesn't stop just because one bubble collapses. Outside this bubble, past a horizon nobody will ever see across, inflation may still be spinning off new pockets of space endlessly. That clock has nothing to do with the one ticking inside ours. A big crunch 20 billion years from now would be true, local, and almost beside the point. The youngness paradox, the measure problem, Guth's two-headed cows, none of it depends on what happens to this one bubble. It depends on what the wider inflating structure outside it is still doing. One door closes, the other stays exactly where it's always been. Past a horizon, past any measurement, past anything a telescope built inside this bubble could ever reach. Here is where the physics runs out. Physicists have spent decades throwing genuinely serious tools at one fundamental question. Given enough time or structure or however many disconnected bubbles of space actually exist, should a mind like yours be common or vanishingly rare? Heat death says wait long enough and rare stops applying. Eternal inflation says space itself may already be doing the waiting. Somewhere past a horizon nobody will ever cross. A cosmological constant that isn't constant complicates both answers, without settling either one. Every fix proposed so far, the scale factor cutoff, the causal diamond measure, a big crunch nobody has confirmed, trades one unresolved problem for a different one. No counting rule currently manages to keep every good result and avoid every bad one at the same time. That's not a gap in this one explanation. It's the honest, current state of an entire field. Cosmology has taken this question about as far as cosmology currently can, which leaves exactly one place left to check. Not outward, at the universe. Inward, at the one piece of evidence you've been trusting this entire time without ever once verifying it, your own memory. Set the multiverse aside for a moment. There's an entirely separate route to the same unsettling place, and it doesn't need inflation, vacuum decay, or infinite bubbles at all. It only needs one very stubborn 17th century philosopher, alone in a room, trying to figure out if there was anything at all he could know for certain. He built the test in stages, each one more radical than the last. First he doubted his senses alone. Eyes and ears get fooled constantly, and everyone already knows it from experience. Then he pushed harder. How do you know, right now, that you aren't dreaming? A vivid dream feels completely real while it's happening, and there's no reliable test you can run from inside it to tell the difference. Even that wasn't extreme enough for what he wanted. So in 1641, in Meditations on First Philosophy, René Descartes pushed one level further still, into a hypothesis built specifically to make even the certainties of mathematics collapse. Assume the worst possible case. Not a world that occasionally fools you, but one built specifically to deceive you. I will suppose, he wrote, that some malicious demon of the utmost power and cunning has employed all his energies in order to deceive me. Under that demon's influence, he continued, the sky, the air, the earth, colours, shapes, sounds, and all external things become nothing but engineered illusions, dreams built to trap his judgment. Descartes wasn't being dramatic for effect. He was hunting for a single fact the demon couldn't fake. He found one. Even a demon powerful enough to fabricate your entire sensory world cannot fabricate the fact that something is currently doing the doubting. This proposition, I am, I exist, he concluded, whenever it is uttered by me or conceived in the mind, is necessarily true. That's not the tidy phrase most people remember from a textbook. The real one, buried in 400-year-old Latin philosophy, is more precise and far more limited than the slogan it eventually got flattened into. More limited, because notice exactly what that proof covers. And notice, just as carefully, what it doesn't. What it covers is a single instant. Something is thinking, right now, therefore something exists, right now, to do the thinking. That's the entire guarantee. Descartes never claimed the demon couldn't touch anything else, and if you take his own thought experiment seriously, it very much can. The demon can still fabricate every memory you're currently holding of 5 minutes ago. It can still fabricate the sense that this thought followed logically from an earlier one, when no earlier moment ever actually happened. The certainty Descartes found only certifies the present tense. Your childhood, your last conversation, the years that made you who you think you are, none of that gets covered by the same guarantee. It's a fortress with exactly one room secured and every hallway leading out of it left completely open. Descartes himself didn't leave that hallway open for long. Over the meditations that follow, he tries to seal it, arguing that a benevolent God would never allow such systematic deception. That guarantee is what finally lets him trust his senses, his memories, the world outside his own mind. Whether that argument actually works is still debated by philosophers 4 centuries later. It matters here for a narrower reason. Descartes assumed there had to be an escape hatch somewhere, some guarantee built into the universe that keeps radical doubt from turning out to be literally true. There's a strange, precise symmetry worth sitting with here. Boltzmann's argument from the very start of this story never claimed a fluctuation had to build an entire universe to be believable from the inside. It only had to build a mind convinced it was standing in one. Descartes reached the same narrow flaw from the opposite direction, armed with nothing but logic. 3 centuries before anyone had the physics to make the argument literal. Physics doesn't offer the same rescue Descartes reached for. A Boltzmann brain doesn't require a demon of infinite power and cunning, patiently constructing false memories on purpose. It only requires patience, and a universe old enough to let random chance do, purely by accident, everything Descartes' demon would have had to engineer deliberately. There's no benevolent guarantee waiting at the end of this version of the argument. Different mechanism, same hallway left wide open, except this time, nobody built a door to close it. The instant is real. What's inside it, nobody ever guaranteed. That gap isn't just philosophy anymore either. There's a direct, replicated experimental demonstration that entirely fabricated autobiographical memories can be built inside a real, healthy human mind, indistinguishable from the inside, from memories of things that actually happened. It started almost by accident, as a class assignment. In 1990, an undergraduate named Jim Cohn, taking a course taught by the psychologist Elizabeth Loftus, tried planting a false memory inside his own family. He wrote up 4 short childhood stories about his younger brother, 3 of them true, 1 invented. It described the brother getting lost in a shopping mall around age 5, then rescued by an elderly stranger and reunited with the family. His brother read all 4. Over the following days, he started recalling the mall incident in his own words, adding details nobody had given him. At the end of the experiment, told that one story was fabricated, he couldn't pick out which one. He didn't believe Cohn when he was told. Loftus and her colleague Jacqueline Pickrell formalized the method in 1995, running it on 24 adult participants. About 25% of them adopted the fabricated mall memory as their own. 5 of the 24, when finally told one story was false, pointed at a true memory instead. Certain the fake one was the one that had actually happened. The false memories weren't flawless copies either, which is its own kind of unsettling. Participants used fewer words to describe the mall incident than they used for their real memories, and rated it as less clear, less vivid. It didn't need to be a perfect copy to be believed. It only needed to be believed. In 2023, a separate team ran a full pre-registered replication of the original study, decades later, on a new set of participants. Roughly 35% adopted the false memory that time, an even higher rate than Loftus and Pickrell originally found. The technique has limits worth knowing too, and the limits are almost as telling as the effect itself. In a follow-up study, the psychologists Kathy Pezdek and Shirley Hodge tried implanting a second kind of false memory, alongside the mall story. The claim that the child had once received a painful, embarrassing enema. Getting lost in a mall is the kind of thing that plausibly happens to any child. Getting a surprise enema from a stranger is not. The mall memory implanted at rates comparable to the original study. The enema memory barely implanted at all. Believability, it turns out, isn't really about how vivid or emotional a false story is. It's about how easily it fits the shape of a life your mind already expects to have had. Nobody in that room needed a demon or a randomly fluctuating patch of vacuum to pull this off. A few printed paragraphs and a few days were enough. Descartes and Loftus both leave you with a working self, just one whose past is impossible to fully verify. There's a further question sitting underneath that one, and a philosopher working 3 centuries after Descartes forced it into the open with a single, deliberately unsettling machine. In 1984, in his book Reasons and Persons, the philosopher Derek Parfit asked you to imagine a teletransporter. Step inside on Earth, and it scans your body down to the last atom, destroys it in the process, and beams the information to Mars. A machine there reconstructs you, atom for atom, in exactly the same configuration. Most people, Parfit found, are willing to call this travel. You walked into a booth, you walked out on Mars. Same person, most would say. Then, he broke the machine on purpose. In his branch line version, the Earth scanner reads your body successfully, but forgets to destroy it. Now, there are 2 of you. One wakes up on Mars with every memory intact, absolutely convinced he is you. One is still standing in the booth on Earth, badly damaged, dying within the hour, equally convinced he is you. They can't both be the single, unbroken continuation of the person who stepped in. Something in the ordinary idea of personal identity just quietly broke. Parfit's own conclusion was blunt. Identity in the strict sense, one continuous thread connecting you at birth to you right now, was never doing the philosophical work everyone assumed it was doing. What matters is something looser, which he called psychological continuity. Memories, intentions, personality, chained together closely enough to count as you for any practical purpose. That relation, unlike strict identity, can branch. It can point at 2 different people at once, or if the scanner had glitched twice, at 3. A Boltzmann brain doesn't even need the branching. It needs less than the teleporter did. The Mars replica, at least, is caused by something, a real scan, of a real person, transmitted deliberately across real distance. A Boltzmann brain arrives holding the identical bundle of memories and continuity, Parfit says, is what actually matters, and no causal thread connecting it to anything at all. By his own definition of what makes someone you, it qualifies. There was simply never anyone on the other end of the wire. That's an uncomfortable place to leave the argument. It gets worse once you try to actually reason your way through it, because the reasoning itself turns out to fight itself. In April 2025, the philosopher Adam Elgar, writing in Philosophy and Phenomenological Research, gave this problem its sharpest formal name: cognitive instability. Here's the shape of the trap, roughly as physicist Sean Carroll first laid it out. Suppose your cosmological evidence really does suggest the universe is large enough to be crawling with Boltzmann brains. Follow that evidence honestly, and you should become confident you're one of them. But a Boltzmann brain's memories were generated at random, not by living a life. Becoming confident you're one means becoming confident your own reasons for believing it are worthless. It's like trusting a clock reading 8:17, then learning the clock is broken and displays a random number every second, and somehow still trusting that it says 8:17. So you flinch back and decide you're probably not a Boltzmann brain after all. Except now you're trusting your memories again, which points you straight back to the cosmological evidence, which points you straight back toward Boltzmann brains dominating. There's no stable place left to stand. Confidence in either direction quietly undermines the reasoning that got you there. We should say plainly, Elgar's own paper argues this trap may be an illusion rather than a genuine dead end. He uses a case about a hallucinogen that scrambles pill bottle labels to show how the math can, under the right conditions, break the loop. Whether that fix actually works for the real Boltzmann brain case still depends on assumptions philosophers openly disagree about. How wide is the range of a Boltzmann brain's possible experiences, really? Is some version of an indifference rule about self-location even true? Elgar isn't the only one working this exact fault line either. Raphael Busso's causal diamond measure, the tool that already settled how many universes get counted, approaches the same problem from black hole physics instead of philosophy of self-locating belief. Same fault line, cracked open from a different angle entirely. The honest state of this argument, as of the year you're watching this, is that professional philosophers are still formally fighting over whether the trap is real, not settled. Just recently, seriously, argued. Let's stop circling the argument in the abstract for a moment, and put it where it actually lives. On you, specifically, right now. Every scar you're carrying has a story attached to it. How you got it, who was there, how much it hurt. Under everything this video has laid out, none of that story is guaranteed to have happened even once. Not the fall that caused the scar, not the person who helped clean the wound, not the version of you who was young enough for it to still heal quickly. A Boltzmann brain that includes exactly that scar, exactly that story, exactly that ache when the weather turns, costs the universe nothing extra to produce. The fluctuation that builds a mind convinced it has a body doesn't need to also build the body's entire 40-year backstory. It only needs to build the conviction. The same goes for smaller things. The weight of someone's arms around you during the best hug you can remember. The specific, physical relief of finally sitting down after a long day. None of it needs to have been lived to be remembered as vividly as if it had. Even something as basic as your own heartbeat carries this problem. The rhythm you can feel in your chest right now, the concrete, physical there-ness of it, doesn't require a heart that's actually been beating for years to produce. It only requires the momentary conviction of one. The horror here was never really about losing your past in some abstract, philosophical sense. It's that the past was never load-bearing to begin with. You never needed it. You only ever needed to feel right now like you had one. I'll say plainly, because staying purely clinical here starts to feel dishonest. Sitting with that thought for more than a few seconds is genuinely unpleasant, and I don't think there's a clever reframe that makes it stop being unpleasant. We're not being shown a ghost story. We're being shown a gap between what your body insists is true and what the argument can actually promise you. Nothing in this video is going to pretend that gap closes just because we finally named it. And if that gap is real for you, specifically, it was never going to stop at the edge of your own skin. That gap doesn't stay contained to you either, once you actually follow it outward. The people you love carry the same problem, from your side of things. Every conversation you've ever had with them, every argument, every quiet moment when nothing needed to be said, exists in your head as a memory. It doesn't exist as an external fact you can independently verify from outside your own mind. If the fluctuation that assembled you also assembled a complete life's worth of a specific person alongside you, it still didn't need that person to have ever existed. It only needed their voice, their specific laugh, the exact weight of their hand, folded into your memory as if they had. This is not a claim that anyone you love isn't real. It's a claim that the specific kind of certainty you'd want, to rule that out completely, was never actually available to you. It never was, even before this video started. Zoom out past the people you personally know, and the same gap doesn't shrink. Everything you believe about human history, every war, every civilization, every fact you'd cite about who built what and when, reached you through the same channel as your personal memories. That channel is testimony, records, and trust, filtered through minds you have no way to step outside of and independently check. A Boltzmann brain doesn't need real history to feel confident it learned real history. It only needs the feeling of having read about it once. Here's where the argument, if you let it, starts eating its own tail. Everything you've just spent the last hour learning, Boltzmann's equations, Guth's notebook, Descartes' demon, Elgar's paper from 2025, arrived in your head as a sequence of claimed facts. All of it was delivered by a voice you have no independent way to verify. If you're taking the argument seriously enough to feel unsettled by it, you're already trusting the exact kind of internal, unverifiable content. It's the same kind this video just spent an hour telling you not to fully trust. We built the trap and then walked you into it, using the only tool available, your own memory of watching it happen. To be clear, none of this is proof that any of it is happening. It's not even meant as one. Nobody involved in this argument from Boltzmann onward has ever claimed that kind of certainty in either direction. What the recursion actually shows is narrower and in a way more honest. There is no vantage point outside your own mind from which you could ever fully check the math. Not for your own memories, not for the person you love, not for this video. I want to step out of the argument structure for a moment and just tell you something plainly, because pretending otherwise would be its own kind of dishonesty. Researching this video meant reading the same sentences and equations for weeks. The kind that don't leave you when you close the laptop. It happened most specifically the night I was drafting the section about scars, the one you heard a few minutes ago. I'd been staring at my own hands for longer than felt normal, running through where each small mark actually came from. For one genuinely strange stretch of time, I couldn't produce the memory fast enough to reassure myself. It came back. It always comes back. But I noticed the gap before it did, and that gap is the entire subject of this video, felt from the inside instead of described from the outside. I want to be careful here. I'm not telling you this to compare it to anything Boltzmann actually went through. His was a real, clinical, decades-long struggle, and this isn't that, and I don't want to borrow the weight of his story to dramatize a few uncomfortable nights of mine. There's a reason I'm including this instead of cutting it in the edit. A cosmic horror documentary only works if the dread on screen is earned somewhere. I'd rather earn it straight in a couple of plain paragraphs than fake it with a dramatic sting over a graphic. If something in this argument is going to unsettle you, I wanted you to know it unsettled the person who spent the most time with it too. I'm telling you all of this because I think it's the honest answer to a question you might already be quietly asking yourself. Does taking this argument seriously actually feel like anything, or is it just an interesting idea to turn over? It does feel like something. It's mild, it's temporary, and it's real. I'm still making this video anyway, obviously, not because the discomfort isn't real, but because I'd rather sit with a real, unresolved unease than a comfortable answer I don't actually believe. That's the trade this whole project keeps asking you to make, and it seemed wrong to ask it of you without admitting I'm making it too. Everything you've just walked through refuses to resolve into either a clean yes or a clean no, and by now that probably isn't a surprise. It didn't resolve in the physics either. Descartes proved you exist for exactly one instant, and left your entire history unguaranteed. Loftus proved, in a lab, with real people, that a fabricated history can be planted and believed as completely as a real one. Parfit showed that the kind of continuity you actually care about was never a special, unbreakable thread to begin with. It's just an ordinary relation that happens to usually run in a straight line. Elgar showed that trying to reason your way out of the resulting uncertainty tends to undermine whichever direction you push. None of these four thinkers were talking to each other. None of them built their argument with Boltzmann brains specifically in mind. Picture four people climbing the same mountain from four different, unconnected faces, centuries apart, never once comparing notes. A physicist working out the odds of gas molecules rearranging themselves. A philosopher inventing a hypothetical demon. A psychologist running a memory experiment with printed booklets. Another philosopher formalizing exactly why the resulting doubt won't sit still. All four reach the same narrow ridge. None of them can see over the other side, and neither, it turns out, can we. This is the same shape you saw in the thermodynamics of a dying universe, and again in the mathematics of an endlessly inflating one. Recognizable each time, dressed differently. Physicists don't treat an excess of Boltzmann brains as proof their models are wrong. They treat it as a diagnostic, a signal that something in the model still needs work. Philosophy, working the same territory from a completely different direction, arrives at an identical posture. Not proof, not disproof, a permanently open diagnostic, running quietly in the background of your own certainty about who you are. That's not a flaw in the argument. The kind a smarter philosopher or a better experiment will eventually patch. At this point, it looks structural, which means the honest place to end isn't relief, and it isn't despair either. It's just recognition held for a moment, before we ask what, if anything, a person is actually supposed to do with it. Go back to the very first thing you heard in this video. What if your life never actually happened? What if the years you spent becoming who you are, the people who raised you, the mistakes you're still carrying around, none of it took place? What if you simply appeared a moment ago, already convinced that it had? You've now spent the better part of 2 hours getting an honest answer to that question, and here it is. I don't have a comforting one for you. Physicists studying the long-term fate of an expanding universe cannot currently rule out that minds like yours are, statistically, vastly outnumbered by minds that assembled themselves from nothing. Philosophers working from a completely different angle keep landing on the same narrow, unguaranteed instant of certainty, with nothing behind it they can prove. Neither field found a clean escape hatch, both left the door standing open. Put a number on how long that door has to stay open, if the earlier math in this video is right. You get something like 10 to the power of 10 to the power of 50 years. That's a span so large it makes the entire recorded history of the human species round down to 0. On the physics side, that's Boltzmann's own equations, run forward by cosmologists like Guth, Linde, and Vilenkin into a genuinely open measure problem nobody has closed. On the philosophy side, that's Descartes' demon, Loftus's fabricated memories, Parfit's broken teleporter, and Elgar's still unresolved instability. 4 separate arguments that never once needed physics to reach an unnervingly similar place. You didn't hear one argument tonight. You heard 2, built centuries apart, agreeing with each other by accident. If you came into this video hoping for a tidy resolution, but don't worry, here's why it's actually fine moment. I want to tell you plainly, it isn't coming. Not because I'm withholding it for dramatic effect. Because nobody currently doing this work, on either side of the aisle, has it to give you. Here's what I do know for certain, and I want to say it slowly, because it's easy to rush past. The measure problem, the one built from Guth's monopolies all the way to Busso's causal diamond, is not a settled piece of history. It is an active, unresolved argument inside cosmology as of today, this year, the one printed at the start of this video. Physicists you could name, working at real universities, are still publishing on it. They still disagree with each other about which counting rule is correct. They still cannot rule out that an excess of randomly assembled minds is the actual, literal prediction of our best current models. Trace the timeline and the pattern is obvious. Dyson, Kleban, and Susskind opened this specific version of the problem in 2002. Guth and his own co-authors were still trying to patch it in 2010. Elgar was still formally wrestling with the resulting instability in 2025. That's 23 years of continuous, serious, published disagreement, and nothing in the current literature suggests that clock is about to stop. Add Raphael Busso's causal diamond measure to that timeline, still being refined and debated as recently as the past few years, and the picture doesn't get any more settled. It gets more crowded. I looked for a version of this story with a tidier ending before I ever started writing it. I read the follow-up papers, the rebuttals, the counter-rebuttals. Every serious attempt to fully close this door ends up trading one open question for a different open question, dressed in slightly different math. That's the cold part, and I'm not going to soften it. Nobody currently has the tools to hand you certainty in either direction. Not confidently in favor, not confidently against. Let me step outside the role of narrator for a second. There's a question that tends to surface right about here, and it deserves a straight answer instead of a dramatic pause. Does any of this change what you should actually do today? No. It doesn't, and it can't. And that's not a cop-out. It's a fact about the structure of the argument itself. If you are a Boltzmann brain, a fluctuation that will likely dissolve back into randomness in the next instant, nothing you decide matters. There is no meaningful future for it to matter in. If you are not an ordinary person with an ordinary causally connected past and a real future ahead of you, the outcome is the same. Everything you already cared about yesterday still deserves exactly the same care today. There is no version of this argument that hands you a reason to act differently, whichever answer turns out to be true. You might be tempted to take the logic one step further and conclude that if nothing you do can be verified as mattering, you're free to stop caring altogether. That conclusion doesn't actually follow, and it's worth being precise about why. Caring about the people in your life was never conditional on first proving, with certainty, that they and their past are exactly what your memory says they are. It never worked that way. For anyone, at any point in human history, long before this argument existed, the argument didn't add a new requirement. It just made an old, quietly ignored gap impossible to unsee. That's not me dodging the weight of the last 2 hours. It's the actual shape of the math. A question can be completely unresolved and completely unable to change a single one of your choices at the same time. Those two facts don't cancel each other out. They just sit next to each other uncomfortably, which is exactly where this video is going to leave them for one more moment before we're done. So here's the last thing I actually want to say to you, and I'm dropping to the documentary voice completely to say it. You might be a person with 40 years of real history behind you, or you might be a fluctuation that assembled itself a few hours ago and will dissolve again shortly. Whichever one you are, one fact remains. Something is reading these words, right now, and finding them worth sitting through to the end. That's not nothing. That's the one thing every argument in this video left standing, untouched, the whole way through. Nobody's math gets to take that away from you. If you're having a good year, I'm genuinely glad. And I mean that plainly, without irony. If you're not, I hope something in your life gets easier soon, and I mean that too. You don't need a settled answer to the question this video opened with in order to deserve either of those things. You already did before you clicked on this video, and you still do now. Thank you for spending 2 hours of a life, real or borrowed. It doesn't actually change this part, on something this strange with me. So let's step back into the story one last time. The way it was always going to end. Somewhere, right now, in an expanding sliver of otherwise empty space, the temperature never quite reaches zero. It sits there, patient, doing almost nothing, for a length of time that makes every number in this video look small by comparison. And every so often, not on any observable schedule, not for any reason anyone is watching for, it produces something. A configuration of matter organized enough to notice itself. Convinced, immediately and completely, that it has always been here. It doesn't announce itself. There's no moment of ignition anyone could point a telescope at and catch in the act. One instant, there is only the faint, patient hum of empty space. The next, something is there that wasn't a moment before, already midway through a thought, already reaching for a memory that was never actually laid down. No sound, no warning. No difference from the outside between this happening once or happening the way it's always happening, somewhere, right now. Whatever you decide to do with the next 5 minutes of your life, physics doesn't need you to resolve any of this first. It just keeps running, the same way it has since long before you started watching, and the same way it will after you close this tab. There is one more thread this video never had time to pull though, and it's the strangest one. If a random fluctuation can build a mind convinced it has a past, there's no obvious reason it has to stop there. Nothing in the math says the fluctuation has to be lonely. Nothing says it has to be small. Nothing technically says it has to be one. That's a different video. I'll see you there.